Everybody already know me. My name's Topher. Oh, and I got a bad pen, so we'll get this out of here. Actually, I'm Mr. Folly, and I'll make my pen a little more reasonable. And hop right to this. My goal here is 1 to 17 as quick as I can. So here's our key. The oxidation of NO producing NO2 gas is represented by the chemical equation shown above, which I wrote my name over. The initial concentration of NO and O2 are given in the table above. Initial, bang, bang. The change in concentration of NO as a function of time are shown in the following graph. So NO and O, first thing I notice is I've got a difference in coefficients. Okay. In the graph below, draw the curve for the rate of disappearance of O2. So this is the concentration of NO. So I've got NO here, which they labeled it just fine. So that means everything here should be half as much. So it starts at half as much, and the change will be half as much. Okay. So 0.014. And then the change for the first one is, let's see, this is 0.02028. I suppose I should look at my OOs a little better. 0028, and then it goes down to 0.0019. So the change there is going to be I'm just going to focus on the 9 part. Okay, so it's going to go 9. So this goes from 14 to half of 9, which is 4.5. That'll be about 10-ish. And that's not going very far. 10-ish, not going very far. The next one would be from 0.0019 to about 0.0013. So that change is going to be in the 6-ish range. So I'm here. I'm going to go to the 6-ish range. I'm lining up these dots. Thank you for making it look nice. Okay. That change is 6. So I went from, just below, I should write mine down. 0014. And then what was my first change was 9. So then I got 0.0009. And then I had to change 6. So I should be at 0.00, half of 6. So I need to change 3, 0.0006. Yeah, so that's where I got my 6 there. Okay. And then the next one, so from 0.013 to 0.0, what is this here? 7. That change is going to be about 6 again. So for us, that's going to be 3. I'm trying to line it up as best I can. And then I get the magic marker fun. And then, why can't it add? You know what? I'm about done with this curve. So, oh no. Would it be half as much? No, it would be less than half as much. So it's half as much and the change is less. Did I do it wrong? I have to double that change, don't I? Oh, nope, half the change. I'm doing it right. So there's 3. So then at that 100 mark, it went from 0.0007 to 0.0005, which is 2. And I'm going to do 1. So I went from 03 to 02. And then I kind of just want to, because it gets really close to the 0 mark. So there you go. I cheated. I admit it, but you got the idea. Consider the combustion of ethylene. If the concentration of C2H4 is decreasing at the rate of 0.036, okay, so that is ethylene is decreasing at 0.036. What are the rates of change in concentration in CO2? So that would be times 2, and H2O times 2. So they're both going to be the same. So that's going to be 0.072 molar per second for both. Why is that? Because the coefficients are double. I'm going to make my pen a little smaller. I'm going to pick a better color. If the rate of decrease of N2H4 partial pressure in a closed reaction vessel blah, 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 is 74 torr per hour. So notice this time we're doing pressure change, which, remember, is proportional to moles and molarity. What's the rate of change on partial pressure and total pressure in the vessel? Okay, so we've got partial pressure and total pressure here. So the rate of decrease of N2H4 is 74. What's the change of the other one? So NH3 would be double. So NH3, 73 times double is 148 torr. What are the rates of change of NH3, partial pressure, and the total pressure in the vessel? Okay, so I'm worried about this one, so I'm going to ice diagram it a little bit. So N2H4 plus H2 yields 2NH. I'm going to make this bigger. 2NH3. Oops, lost my penniness. 2NH3. So I'm going to start off with, it says total pressure change. So what I'm going to start with is I'll just start out and say I have 70. Well, let's double it to make it easier. Well, let's do easy numbers. 100, 100, 0. Yeah, and that's it. So if this is minus 74, this would be minus 74. This was plus 148. So you notice how this change cancels out because I have a coefficient of 1 and a coefficient of 1. So what's the change of the total pressure change? It goes up. Well, I guess it goes down. 1 down 148. And it goes up 148. And I just picked whatever number to have it fly, and that works. At a certain time during the titration, the rate of appearance of O2 was, boom, I got myself a rate. What is the rate of disappearance of MnO4 at the same time? So O2 is this number right here. And then disappearance of permanganate is, okay, so I'll show a little more work than I did for the other ones. 2.5 E negative 3 molar per second of O2 times, it would be 5O2 into MnO4 negative, which of course is an intense purple color. So that's going to be 2 times 2.5 is 5 divided by 5. So I'm going to get 1 E negative 3 molar permanganate. Molar per second. And notice the O2 canceled, MnO4 stayed, so I have molarity per second, which is the same thing as moles per liter. That's molarity per second. Okay. What is the rate of appearance of Mn plus 2 at the same time? Mn plus 2 has the same coefficient as permanganate, 1 E negative 3. I'll write it the way they did, mole per liter seconds for Mn plus 2. And then some work is expected because same coef as MnO4 negative. As time progresses, would you expect the rate of disappearance of MnO4 to increase, decrease, or remain the same? Rate of disappearance of MnO4. So I start off with decrease in rate. There are fewer moles in same volume. Oops. So fewer collisions and fewer successful collisions. Man, this collision theory is annoying. So rate is lower. All right. Well, that will be a good spot to stop. Well, pause.